Hola amigos! Today's video is gonna be the first in a multi-part series where we're going to create some high-quality cinematic VFX inspired by your favorite anime and Hollywood movies. Our final goal is to create a high-power magical effect from scratch, consisting of a base projectile with different trails, an explosion, and some pre-animated assets. Most of the stuff like textures or meshes that I will use are available on the engine or sample content folders, but anytime I use a custom asset, like these Houdini pre-calculated destruction animations, I will make those freely available. We'll kick off the effect by creating this interactive lining that seeks out points or nearby surfaces to attach to. If you're not a Niagara expert, don't worry, this first tutorial will be relatively easy and will go step by step. So when things start to pick up speed by the third video or so, you'll be very familiar with these systems. Start by creating an actor blueprint. This one will be our primary projectile and the source for most of the effects. After giving it a name, I called it lightning ball, the first thing we'll do is add a reference sphere just to have an idea of the size we want. We can leave the default material for now, we'll make something much more interesting in the next video. I'll make the sphere a bit smaller, uniformly setting the scale to 0.25. In the future, we'll also replace the mesh with something that we can deform, but again, this is just for size reference. Next, we're going to add a function call to the event tick, but first I want to create a few blueprint variables so we can adjust some of the effect parameters from it. Today we'll need 4 float variables. The first two, trace cooldown and last trace, will be used to control how often the lighting happens. The other two, min and max radius, will control the starting point and how far they can reach away from the source. Next, create a new function and add a call to it right after the event tick. I call this one update traces. Let's jump right into it. The first part of this update function is to check if the cooldown time has expired so we can fire another line trace. Here's a very simple way to do this. Get the current time in seconds and subtract it from the value that we stored when the last trace happened. If that number is equal or greater than the cooldown time, then the next trace is ready. We can then add a print string to confirm that it works, but don't forget to update the last trace time before or after this. After setting some default values, we can give this a try. And here it is. As expected, the lightning ball is greeting us with a nice hello every half a second. Now we can go back to the function and replace the debug print with our line trace searching for a collision point. As usual, the most important parameters of this raycast are the start and end points. Since we're going to use a spherical distribution, we can get a random direction and simply get a couple points from the center along it. Note that when using random nodes like this one more than once, you will have to promote them to a variable, otherwise you will be getting a new random value each time that the node is connected. Now, with a random direction set, we can multiply it by the minimum radius and add it to this actor's location. This is going to be the start point of our line trace. The endpoint will be set in the same way, except that we are going to use the maximum radius variable instead. We can duplicate all the previous nodes and swap the variable to save a bit of time here. Note that these two locations, start and endpoint, are in world space, and we'll keep them that way. Later on, one of our particle systems will use a local offset instead of the absolute position, but we can easily get that if we just take the multiplication value without adding it to the actor's location. I've also enabled the debug draw for the line trace and set the draw duration to be our cooldown variable. That way, we'll get a pretty good visual representation of how frequent the lighting is gonna happen. Set the minimum radius to approximate the size of the sphere, and the maximum to something like 200 or 300. This will give us a decent distance for the raycasts. After that, we can give all these nodes their own comment box and test it in the viewport. And here are imaginary still lightning bolts. As you can see, many of these are not reaching all the way across to a valid surface, which is exactly what we want. Once we start working on the projectile in the next video, we'll add some surrounding lighting so there's always some of it present even when there is not a lot of geometry around. And now it is time to create our first Niagara system, using the dynamic beam as a meter template. I've called this one lining arcs and we'll come back to it in just a moment. But first, let's make our update traces function spawn one of those whenever there is a valid hit. We will spawn the Niagara system attached to the default scene root after setting the last trace variable. No worries, I'll fix this one in a moment. The reason is that we always want to reset the cooldown after a line trace, but only spawn the Niagara system if there is a hit. That way, the graph will be a bit better organized. After adding a comment box around these nodes, we can break the hit result and add a branch to only spawn the Niagara effect when there was a hit. Then set the default scene root as the component to attach this system to. Don't forget to set the template property to the system that we just created. And one thing to note is that we are not spawning the effect at the collision point, but at the actor's root, by keeping the location as 000. This is because we are going to pass this information as parameters to the system and let the emitters handle it in different ways. Speaking of which, let's go back to Niagara and change the emitter to play only once, and then change the loop duration to 2. Since the lighting effect is going to last less than a second, that will give it plenty of time for any lingering particles to finish properly before removing the system. We will also remove the beam width and the solve forces and velocity modules from the emitter, and then add 3 vector variables to the user parameter section: beam start point, beam end point, and impact normal. Before we can use those parameters though, let's head over to the blueprint to give them some values. Add 3 copies of the setNiagara variable, vector3, connect their targets, and set the variable names to the 3 ones that we just added to the system. Now we can set their values. Beam start point is set to the product of the random direction and the minimum radius. That is, the local start position of the beam relative to the actor's root. We could use the absolute world location instead, but this will make some things easier in the future. Beam endpoint is set to the impact location from the line trace hit information. And finally, impact normal is straight up the impact normal from the hit. We will use this value to set some of the secondary effects directions later on. Remember that you can organize graph connections by double-clicking on any of them to add a reroute node. Give me a moment to do that and fix this spaghetti mess that I have here and make things easier for you to read. Here's the graph so far. We're actually going to make a quick change on the beam endpoint before we use it though. You see, I realized that some of the effects that I'm planning on showing will cause artifacts if they spawn right on top of the geometry. So we're going to use the normal to offset the endpoint a little bit in that direction. We can do that by multiplying the normal by a factor before adding it to the impact location. A small value will work here. We just want to avoid having our target be exactly on the mesh, but not far enough to have a visible gap. After giving this part a big old comment box, we can give this a test, but there's not much to say yet. We're passing these values to the Niagara system, but the emitter is not doing anything with them. And as promised, here's the default dynamic beam emitter doing a bunch of nothing. Let's fix that. Go back to the Niagara editor and in the beam emitter setup module, replace the start and end values with our user parameters. You can drag and drop those from the bottom left panel to the properties list on the right. Here we also have to disable the absolute beam start checkbox and enable the absolute beam end 1 to match the setup that we have on the projectile blueprint. That should do it. If you give it another try now, you should have something similar to this. with thin blue lines matching the line trace's location. We still have a lot of work to do on this, but since we can finally visualize our effect, we should go back to the blueprint and disable the debug trace to make things a bit nicer while we do the next part. There are many ways to achieve the jagged effect of lightning bolts with particles. I've seen a lot of people do it with a curl noise force, but since the particles are being respawned every frame directly on the line, this requires setting the intensity to crazy high values, which can mess with other parts of the effect later on. In my opinion, the best way to do it is with an expression, and we'll come back to this in a future video, but for today we'll use a jitter position module. This will directly override the position attribute on the particles, so we don't have to rely on the forces and velocity solver to move them around. Let's try again now. Yeah, this is an interesting effect, but it's clearly not what we're looking for. These lines are very curvy and twisted, and have too much detail for the type of lighting that we want to achieve. Fortunately, the solution comes in two simple steps. The first one is to reduce the number of total particles that we are spawning. Something like 20 or 30 should be enough for the average length of these arcs. The second one is a small adjustment on the ribbon renderer parameters under the tessellation section. You can either increase the curve tension to a value close to 1 or disable it entirely. After these two changes, our beam should be formed by a smaller number of particles connected with straight lines. We could spend some time adjusting these settings to get a slightly more detailed arc that still looks like lightning, but this looks good enough for now, so we can move on to the next part. There is a parameter on the beam emitter setup module that we haven't looked at yet, called Use Beam Tangents. Once you enable it, two things are gonna happen. First, the arcs are gonna become a bit wild and curve in weird ways. And second, a few new parameters will show up in the module. These allow us to control the direction of the beam tangents, which we will use to make the effect arc upwards, like in those Jacob's ladder voltage converters. Before doing that though, let's set the lifetime of the effect to 0.5 seconds and the cooldown between arcs to 0.2 on the blueprint, so we don't have more than 3 simultaneous bolts. Let's give this a try. Perfect. With the timing adjusted, we can go back to playing with tangents. This is what we're going to do. We don't want the arc's curve to go inside the sphere, so we're going to disable the effect of the beam start tangent, setting the multiplier value to 0. Then we'll bend the beam from the end point instead, setting its tangent to a vertical vector, that is 0, 0, 1, and increasing the multiplier value over time using a curve. We can use the 0 to 1 S-curve template and keep the default normalized loop H as the index. To adjust the intensity of the effect, we can scale the curve with the parameter below. A value of 5 or 6 will produce a good upwards motion that doesn't bend the lightning bolts too much, but we can always come back and tune these settings. It is time to add a bit of color to the effect. Go to the Initialize Particle module and change the color mode to Direct Set. Then change the source to Color from Curve. Change the mode to Gradient if it's not set by default, and set a continuous opacity of 1. Let's make a nice gradient. I'm going to set a few variations of a light blue color distributed along the whole curve. Then add a slightly purple point on one of the ends and a very bright blue on the other. Since we are going to assign a random color from this gradient to each section of the beam, I want mine to be mostly light blue with some color variation and just a few extremely bright hotspots. But feel free to spend some time editing this gradient to your heart's content. Just remember that once we're done setting it up, the frequency of the different random colors in the effect will be proportional to the distribution in this gradient. While we're in this module, we can give some variation to the ribbon width. We can do it here in the ribbon attributes section, setting a random value, or use the module that we removed earlier, set beam width, and achieve exactly the same result. If we use the ribbon link order property from each particle, we can give each segment a slightly increase in width over the length of the beam. I think I inverted this later when I was tweaking my settings, to have the width be still a bit randomized but decreasing from a start point to the impact instead of the opposite. We'll probably come back to it once we start looking at HLSL expressions in the future, so don't sweat it. Let's give this a try to see how we're doing so far. Looking good, we can see some width variation, but the color is still blue. That is because of two reasons. First, there's a color module that I forgot to remove and it's overriding the color set on spawn. But I also didn't change the curve index, which by default is set to the normalized edge of the particles. After setting it to a random value from 0 to 1, we can give it another try. Excellent, this is starting to look like something. The color variation is showing up, and every now and then we get one or two of those bright spots. These colors are not changing over time though, so it's time to add a scale color module and correct that. We will have a simple alpha scale using a curve that will keep the opacity around 1 for most of the arc's life and fade right at the end. The more interesting stuff is going to happen in the RGB scale, where we're going to ping-pong the value up and down over time, slowly converging to a small number before spiking right at the end. Also, we might tweak the color channels individually in the future, but for now I will scale a 1-1-1 vector using a float curve. At this point I spent a bit of time editing this curve, and I went back to it one more time off camera after making the video. This is another one of those things that you can spend hours tweaking and improving, adding subtle variations and changes. However, I'll spare you of all of that and skip right to the result, so you can get an idea of what I wanted to achieve. Here's what I had by this time. In my latest version, I added a few more nodes, scaled them so the curve tapers towards a low value, and added a bright spike right at the end, but this is pretty close to that. One of the fun aspects about lighting and magic VFX is that they can be quite chaotic, so don't be shy about experimenting and trying new things. Next, we're going to make a very quick and simple material for these ribbons. We will work more on it on the next video, where we will make new materials for all these particle effects from scratch. For this one today, enable the Use with Niagara ribbons checkbox on the properties. Set also the blend mode to additive and the shading model to unlit. We want the lining to be emissive only and add it to the final color. Since we will make new materials in the next tutorial, I won't go over this one in extreme detail, but the basic idea is to use the particle color as emissive, and for opacity we will take the green component of the UVs and mirror it, using a 1- to invert the values and then a power to compress the range afterwards. This will give us a mirrored vertical gradient that starts in the center of the texture and spreads in both directions. Finally, we can multiply this value by the particle color's alpha channel and output the result. All this is to make the material bilaterally symmetrical and the lining a bit nicer, but we won't need it once we switch to a static texture in the next video, so feel free to skip a few seconds ahead while I finish making this graph. Back in Niagara, all we have to do is replace the default ribbon material with this one and check out the differences. I've also changed the way the UVs are mapped to the ribbon, but for this simple material it shouldn't affect the results. It might be a bit hard to see at this scale, but it looks like the material is correctly mapped and it fades symmetrically towards both sides. Now, for the rest of the video, we will create a few secondary emitters to add more pizzazz to the main lining, starting with some impact hotspots. We can use almost any emitter template, since we're going to remove many of its modules. And like in the previous emitter, the first thing to do is set the behavior to loop only once and the duration to 2 seconds. These settings will be the same for all the emitters in this system. Next, set the spawn to be an instantaneous burst with a count of 1, instead of a spawn rate, and remove the shape location. We're going to set the position of this single particle directly copying the value from the beam endpoint user parameter. If you drag and drop it from the panel, Unreal will automatically convert the variable type from vector to position. And since we added an offset along the normal direction earlier, we shouldn't have set fighting issues with these particles. Let's increase the sprite size to something like 15 or 20 so we can clearly see them and give this a try. Yeah, we should have first removed all the physics modules from the stack. Let's say gravity force, drag, and solid forces and velocity can all go away. We want this particle to stay right where it's spawned. Okay, this is better, but the sprite is facing the camera. We want it to behave instead almost like a decal, and be oriented flat to the surface that it's sitting on. Thankfully, the solution is quite simple. In the sprite renderer, we'll change the alignment to custom, and set the facing mode to custom vector. Then, on the binding section at the bottom of the panel, find the sprite facing binding and replace the value there with our impact normal user parameter. This should make the spots appear flat now. Let's check them out. Great. Now all we have left to do is to tweak some of the emitter parameters to make these sprites look a bit better. I'll reduce the particle lifetime quite a bit and set their color to a bright blue to match the rest of the effects. Since we're spawning a single particle, we can also afford to add a light renderer without increasing the cost too much. Note that if you disable the inverse square fall-off property on the light renderer, you will have more control over the lights, but you will also have to increase the exponent value to avoid having hard edges on them, as we can see happening here. A couple tweaks to the radius and exponent settings will fix that. Here I'm using 4 and 8 values respectively, since I wanted medium-size, very diffuse lights. Here they are looking a lot better. Now, similar to what we did for the ribbons, we are going to create a simple placeholder material for these sprites, until we can make something more advanced in the next video. I will quickly go over this one. It is basically a simplified copy of the default sprite material with zero hardness on the sphere mask, to give these circles a softer edge. After copying the nose from the other material, that's kind of it. Like I said, I was gonna keep it simple, but it will be good to have already a foundation to start working on when we get to it. Back in Niagara, we can replace the material in the sprite renderer, and while the change is subtle, it will be good to have a separate copy of the material that we can modify without changing the default one. The effect is getting some life now, but we can still add more layers to it. Remember that many of the individual single pieces that make the cool effects from action movies these days are not that complicated. It's the combination of tens or sometimes hundreds of elements in a VFX shot what makes them shine. The second to last part of the lightning arc element in our projectile today is going to be adding some classic sparks around the impact point. This will help sell in the hotspots spawned by the previous emitter. I will be using a directional burst emitter as template and add a sphere location with a tiny radius where I'm going to also change the shape origin to be the impact point. Technically, we should be using a hemisphere instead, but we can live with that for now. I've also kept the add velocity module, but changed the cone axis to use the impact normal value and increase the angle to 90 degrees. This will give the particles an initial velocity away from the impact surface, which is what we're looking for. To make the sparks appear a bit floatier, we can increase their drag coefficient. And before making more changes to this effect, let's see it in action. This is pretty close to what we want. We are just going to make a few minor adjustments in some of the modules, which we will review next. First, I changed the color to match the rest of the effect, but after looking at it for a while, I decided to lower the saturation and make it almost white for the version in the intro part of the video. That one has a collision module as well, but note that in CPU particles it only supports the ray tracing method, so it becomes a bit more expensive. I also changed the min and max factors on the scale sprite size by speed module to make the sparks a bit longer while they are in motion. Then, after giving it a quick test, I reduced the sprite size to have a more detailed effect. And that's the extent of the changes to this emitter. Not all of them need complicated math or HLSL code. We've got pretty far with the single line beam that we started with, and we haven't finished yet. Like I just mentioned, I think these sparks are too saturated in color, but I'll let you fine-tune the settings of your own version of the effect. But now, for the final layer of the lightning bolts, we're going to add a few lingering particles along the trajectory of the arc, slowly floating upwards as they fade out. Combined with the flickering of the lightning at the end of its life, this will give these bolts a bit more visual persistence without adding lots of noise. Like the previous emitter, we'll base this one off the directional burst template. However, instead of the instantaneous burst, we'll spawn particles from other emitter, in our case the main beam effect. We also have to reverse the gravity and lower its value, so the particles float slowly upwards, and then add a curled noise force, so their movement is a bit more chaotic. Remember that when spawning particles sampling other emitters, having a high spawn rate can make things get out of control easily, leading to performance problems. In our case, the number of particles for the whole system is quite small, so we should be fine even when all the lightning bolts are visible at the same time. Another change that we have to make, since our emitter is not using persistent IDs, is to set the sampling mode to random in the sampled particles from other emitter module. Otherwise, all of the particles in this one will spawn close to the origin of the beam. And by this point you should be already used to the rest of my changes. I've set the lifetime to be a bit higher than the sparks and the hotspot, so these floaters persist for a longer time. I also changed the color to blue, although I didn't make this one as bright as the others. Since the effect remains on screen for a bit more time, I didn't want to overdo it. For this same reason, I made the minimum random size of them quite tiny. Then, I increased the drag, and played with the settings of the curl noise force to get a subtle effect on the particles' motion and not send them speeding all over the place. I think I made a few other changes off camera, but those were just minor tweaks to balance everything out. And with this fourth effect layer, I think that is enough for this line effect, at least for today. If you stayed until the end, thank you for watching this video, and congratulations on completing the first chapter of this tutorial series. In the next video, we will add a secondary branching spark to our lightning bolts, and maybe we will start working on their main projectile trail if we have the time, but it will be mostly focused on making some advanced materials for the emitters that we made today. If you like the content, consider subscribing and clicking that like button down there. It helps a lot giving the video some visibility. See you next time!